This is a problem where we are given a few oranges. Some of them are rotten, some of them are fresh. And we are asked to calculate in how much time all the fresh oranges will get rotten. And this is a question which has been very frequently asked in Amazon interviews. And at least 120 people have reported that they have actually faced it in their Amazon interviews. So let's see what is the problem. So we are given a grid like this, 2D grid. And some oranges will be rotten, which I will denote by this color. So let's see, this is the rotten orange, and this is fresh orange, as you can see. So this is the initial state at time equal to 0. And one rotten orange will spoil all its neighbors in the next time step. So if this is the state at time equal to 0, here we have just one rotten orange, but we can have multiple. So you can guess what are the oranges that will be spoiled in the next time t equal to 1. And here neighborhood, we will always look in 4 directions: top, down, bottom, left. So this is the question. So can you make any guess what will be the state at t equal to 1? So this is the state at t equal to 1, and you can see that these were the neighbors. This is to the right, this is to the bottom. So these are spoiled at t equal to 1. Now we will not be concerned with this, because whatever was in the neighborhood of this, the original rotten orange, it has already spoiled all its neighbors. So in the next time step, it will have no role to play. These are the freshly rotten oranges. So we have to look at its neighborhood. So at time equal to t, let's see what are in its neighborhood. For this is in neighborhood, and this is also in neighborhood of this, and this is also in neighborhood of this. So if it's neighborhood of multiple, then it doesn't matter from which you have taken this. So in time equal to 2, only these two are in the contact. So these two should be rotten. So let's see at time equal to 2. So you can see that these are rotten. Now we have just one fresh orange that is in contact with any rotten orange at time equal to 2. So only this one should be impacted. And you can see this is now rotten. And in the next time step, this will be rotten, which is here. So at time equal to 4, every orange has been rotten. So we will return 4 in this case. We have to return this. We cannot get all oranges rotten before time equal to 4, since only this can spoil the oranges which are in the immediate neighborhood of this. So it will take at least 4 units here. But there may be some scenarios where not all oranges may be rotten. For example, let's say this orange was, so there were some oranges. Let's say there was a fresh orange here, and there was a rotten orange here, and maybe here. So these rotten oranges cannot spoil this one, since there is nothing in the neighborhood of this. So all these 4 neighborhoods are empty. So in this case, we will return -1, if not all the oranges can be rotten. So how can we proceed here? So it looks like a graph problem. We have some nodes. These grid cells denote nodes. Some of them may be empty, where we are not supposed to visit. The fresh oranges can be treated as unvisited nodes, and the oranges which have just rotten in the previous time step, we will consider them in the queue. So what should we use here? So if you look at the problem statement itself, that is a node, a rotten orange can spoil all its neighbors in the next time step. So straight away you should think of breadth first search, since the definition of breadth first search is that from a given node, in the next time step, you will visit all the neighbors which are at 1 unit distance from it. And in the next time step, you will explore all the neighbors which are 2 units away from them, and those will be triggered by these neighbors. So exact same problem is here, and we can have multiple nodes initially which are rotten. So we have to keep track of all the nodes from where we have to trigger BFS, breadth first search. So what we will do, let's see how we can solve it. So whatever oranges are rotten, we put them into a queue. So in this case, we will just put this one. So let's denote the oranges in queue with some color, let's say blue. So this is in queue at time equal to 0. So at time equal to 0, these are in the queue. So while queue is not empty, so we will use something similar to BFS. what we have to do, we will see how many elements are there in the queue. So we have 1. So we will pop this and then look at its neighbors. So this is its neighbor. So this will be now rotten. So let's insert it into the queue. So this is now inserted in the queue, and this also, and this is now removed from the queue. So we are only interested in this one, since this has already spoiled these two, and now in the next time step this is irrelevant to us. It cannot further spoil. It has already spoiled these two, and now these two are the ones which will contaminate other oranges. So again these two will be in the queue, so queue is not empty. So we also keep track of time. So here we incremented time, and now these two are in the queue, so we will pop them 2 times since we know that size is 2. So we will pop this one and contaminate this one and this one. Next we pop. So this is done. So let's color it with this thing. So we are done with these popped from the queue. And then we will pop this one, and this neighbor is already contaminated. So we are done with this. Now in the queue we have these two oranges. Again we incremented time, so time becomes now 2. And we will pop these two. We pop this one, but there is no neighbor which is fresh. So we are done with this. And then we pop this one. We got one neighbor which is fresh, so we contaminate it. And we are done with this also. Now this is the only orange in the queue, and its time is 3. Then we pop this one and look at its fresh neighbors. So this is the only fresh neighbor, so we contaminate it and push it into the queue, and we are done with this. And now time is 4. So we will increment time whenever we have inserted the new oranges. Now we will pop this one. There is no orange to be contaminated, so in this case we will not increment the time, and we are also done with this. Now the queue becomes empty and we return the time, which is 4. So this is how we will solve the problem. So let's see. Then there is one more scenario that I had said that we may have to return -1 if some orange was not reachable from the spoiled orange. So how we will do that? So let's while looking for a spoiled oranges, the first step where we inserted the originally spoiled oranges into the queue, there also we will compare if it's a fresh orange or not. If it's fresh, we keep track of its count, and then we keep track of how many oranges we contaminated, so that we will keep decrementing the fresh here. So whenever we are contaminating an orange, we decrement the count of fresh. And finally, what we need to do, if fresh is 0, that means we have contaminated exactly this number of oranges, then return this time which we were incrementing, else return -1. So this is very simple. If you understand it, it should be very easy to write the code. So let's begin writing the code. And what should be the time complexity? Let's first see this. So we traverse this grid once to find which oranges are contaminated. So that takes O of n time in the beginning. So here n is the number of oranges. So you can say n equal to r cross c, number of grid cells, not the oranges. So we scan through it once, find the contaminated oranges, push it into the queue. Then we pop this and look at its neighbors. So there can be at max 4 neighbors. And same orange will never be inserted into the queue again. So the orange which was contaminated in the previous time step, we will never insert that again, since that can never contaminate any orange. So an orange is never inserted twice in the queue. So again we can have n time, some factor of n, looking at all the 4 neighbors. So worst case, again it's O of n, and space can be O of n, since in the queue we can insert maybe all oranges are contaminated, so we will insert all of them. So space can also be O of n, and time is also O of n. So now let's write the code for this. So you can go through this. There are three states that are possible for a grid cell. One is empty. Empty means 0. 1 means fresh. 2 means rotten. So these are the three states. So let's have a queue. So this pair for keeping track of coordinates. So I said that we will insert these contaminated oranges in the queue. So by that we meant we will insert the coordinates of these oranges. So we will have row and column number. So that's why I am keeping a pair. And this will always contain the freshly rotten oranges. Fresh equal to 0, we will calculate it while iterating through this grid. T equal to 0 since the time step is initially 0. If it's 2, that is it's rotten, then we insert it into the queue. If it's 1, then it's fresh, so we increment the fresh count. So again we are keeping track of how many fresh oranges were there, so that whenever we contaminate an orange, we will decrement the fresh count. And finally fresh should be 0. Then we will return the time step t, otherwise we will return -1. So let's pick the x and y coordinates. X is rotten dot front dot first. So this rotten holds pair. First is the x coordinate and second is the y coordinate, or the row and column you can say. Then we pop it. Then we will look at all the 4 neighbors. So first neighbor can be x plus 1. So we are checking if x is more than 0, then only we can look at x minus 1. If it's 0, we will not look at that neighbor. And if it's 1, then only we are interested. This is the fresh orange. So we contaminated it, so we are labeling it 2. And then fresh minus minus, since we contaminated it, the count of fresh decreases by 1. And rotten dot push this new coordinate, that is x minus 1 y. And this we will do for all the 4 neighbors. So we are doing exact same thing. You can run a for loop for 0 to 3. And you can save these directions in a pair like -1 0 and so on, but for simplicity I will write it 4 times, although this is not that great. Similarly for y, then x less than or -1. And finally y less than c minus 1. And if we actually did rot any orange, then only we will increment the time step. If we did not make any progress, that is we did not find any fresh orange in this, then this rotten will be empty by the end of this loop. So if we did any progress, then only we will increment the time. Otherwise, either every orange has been rotten or we cannot proceed further. So if not rotten dot empty, then t++, and finally return fresh is equal to 0. That is, we were able to contaminate every orange. Then we return the time taken, else -1. So this is just first is not a function. These are first and second. Rotten.push line 18. Now it works, it's giving 4. Let's try this one. It should give -1. And then we have so it's correct for all these three. So let's go ahead and submit. And the solution is accepted. So we are right here in the top, around 96% of the accepted submissions, just because our runtime is O of n and we cannot do better than this. So now let's repeat this logic in Java and Python. So instead of pair of ints, we can take int array. And the Java solution is also accepted. And here also we are right here in the top. Finally, we will do it in Python 3. So we can use a list as a queue. So these are rows and columns, and fresh will keep the count of fresh oranges. T is the time step, and we will increment every time we contaminate any orange. So we have to pop from the beginning. And the Java Python 3 solution is also accepted.